Okay guys, welcome to this lecture. I really did not expect such a big crowd from first years. I hope you won't get depressed after this lecture. So the topic of this lecture is topology and differential geometry. So the first question arises, why the hell are we studying this? The answer is obvious, because it is required in general relativity. But that is an answer from a physics point of view. Why do people in math study this? So what people in math do is they have a set, let's call the set M, and they want to give some structure to the set. So we define structures like vector spaces. You must know what a vector space is, right? So a vector space is a structure with a set, an addition operation, and a scalar multiplication operation. So this is a structure. The set is there along with two maps. The plus operation is a map which takes from the vector the two components, like vector space plus vector space, again to the vector space, and the scalar multiplication is an operation which takes from the field on which the vector space is defined. It takes one number from the field on which the vector space is defined, another from the vector space, and gives a resultant in the vector space. Similarly, you have heard about groups, I think. Have all of you heard about groups? Okay, then let us leave that. You must have heard about fields, right? So a field is also a structure. It has, again, this, a set F, an operation plus, and a multiplication dot. This multiplication is different from this multiplication of vector space. You must know, right? So plus is a map from F cross F to F, and dot is also a map from F cross F to F. Topology is again a structure on the sets. But why do we really need the structure? So the short answer is, we wanted to generalize the definitions of convergence and continuity to all sets, to like some sets. We wanted to generalize that notion. So you know about the definitions of continuity in Rn, right? Rn, something like that. So I won't write the general definition, but it says that like something like this. If a function, I will write it slightly better. So a function fx, here f is a vector. Okay, so it is an element of some set Rm. Okay, so it is an element of Rn, you can say that. It is f maps, not f is not a vector, fx is a vector. F maps from Rn to Rn. Okay, so we say that the function fx, like when x goes to some x naught, the function fx converges to some f naught if this holds, something like this holds. You know this definition, right? This is correct, right? If
here we just need to converge to some f naught, not necessarily f of x.
It mostly converges to that. That is, wait, I am doing something wrong. Yeah, that is continuity. It converges to f of x naught. I should have written this in my notes. So what I am saying basically is the epsilon delta definition. People know that, right? I may have said something wrong here because I don't remember it correctly. But what the essence of the definition is that if your variable is in some epsilon open interval of the domain, then the function goes to some delta open interval of what is it being mapped to. So you have x naught here, f of x naught here. If you take any x value which is epsilon close to x naught, then it always goes to some delta value close to f of x naught. Now, are people getting, like, just ignore? ignore this conversation. I might have said something wrong here. People know this definition, right? Hello? Any doubts? Fine. So, you see the definition of continuity relies heavily on this concept of open intervals. In topology, what we do is we generalize this notion of open interval to something called open sets. And on those open sets, we define continuity. Similarly, we define convergence also. I won't talk about convergence in detail in this series because we mostly don't need that for physics. So, let me now rigorously define the definition of topology. But you get the idea, right? What we want to do. Yeah, we want to just generalize the definition of open intervals. So, sorry for my handwriting. Let X be a set. A topology on X. Is this visible? So let X be a set. A topology on X is a set. So a topology is again a set. We will call it T. So you see, in these things like a vector space and fields, what the structure we are giving is that of functions. Plus is a function, dot is a function. But in a topological space, the structure we are giving is of another set. So a topology on X is a set which has some properties. So first of all, the topology is a subset of the power set of X. You all know what a power set is? It is a subset of power set of X. And it satisfies the following criteria. That's that. Uncountable. Okay, I got your point.
Mostly topological space and uncountable space. So उसके लिए कैसे define होता है? ये definition
Could still define a power set for uncountable set. Could still define the power set for uncountable set. It will be uncountable. Like, okay, you don't think it has that. I will have to think about that. Okay, let's come back to the definition. So we have a set X. A topology on set X is another set T, which is a subset of power set of X, which satisfies first. The topology must contain the set phi, the null set. It should also contain the set X. If we have two sets U, V, which belongs to the topology, then their intersection must also belong to the topology. Now you could generalize this definition further. So if you have two sets UV, they belong to the topology, their intersection belongs. Now because this is again a set of the topology, take another set W here and its intersection with this complete set belongs to the topology. So you could generalize this to any finite number of intersections. Third, if I have a collection of sets indexed by this alpha, where alpha belongs to some set A, all of which belong to the set T. Okay, so all of the sets U alpha belong to the topology. So, and I form a set using all those sets. Okay, so this should be a subset of topology. Then union of all those sets belong to the topology. Why have I used such a weird notation here instead of just writing if u1, if u comma v belongs to topology, then u union v belongs to topology? Because this holds for countably infinite or uncountably infinite cases also. So I can take infinite sets which belong to the topology and take union of each, and that set should also belong to the topology.
How do you do the indexing on an uncountable collection?
So that's why like the indexing is not done as numbers. That's why I wrote some alpha which alpha belongs to some set A. This is not natural.
So if A is itself an uncountable set, then it becomes an uncountable set.
Yeah. Like you map to some ordinal number or two. Okay. So guys, you get the definition. The definition might seem a bit abstract. It won't seem it is actually a bit abstract, but you will get used to it, and we will see how this becomes useful. So first of all, okay. So I've written topological space here. So a topological space is basically the set X along with a topology T. So it is the structure I was talking about. So I have a set X, I equip with topology T defined like this. Okay. Now the sets which belong to the T, the sets belonging to topology are called the open sets. Okay.
Is this a straightforward generalization of open
We will talk about that later. Okay. I will come to that point. So, given a topological space X comma T, a subset S of X is called open if S belongs to topology. Okay? And a subset, let's call it T, a subset of X called T is called closed if X subtracted from, like, T subtracted from X belongs to topology. So a subset is open, a subset of X is open if it belongs to the topology, and it is closed if it subtracted from the total set belongs to the topology. Now I will give you an example so that you could actually understand what is going on. So let us take our set to be now. You have to. I will write some topologies T. You have to tell me which is actually a topology and which is not. So I will write some sets which are subsets of the power set of X. You just have to tell me which are topologies. Is this a topology on X? Anyone saying no? You aren't able to see this. Okay, I will write it somewhere. anyone saying no that this is not a topology? So all of you are agreeing with that this is a topology? Okay. So yeah, this is a topology. Yes. Consider this. Is this a topology? Why not? Who is saying no? Why?
Okay, sorry.
Intersection of B and BC is not there. Correct. It is not a topology. No, wait.
It's present, right?
Sorry. Yeah, it is a topology. I have written no here. I don't know why. I think it should be C here. Then it won't be a topology. Yeah, so that is a topology. Okay, one more example. Is this a topology? Very good. I will give some time to think about this. So yeah, it is a topology. Any doubts till now? Okay. So let's move on. So I want to come back to this point of open and closed sets. So okay, let's do one more example here.
I have a doubt about the union property.
Yeah.
If we allow for infinite number of unions, would we have a theorem that we can always find a closed set that's of that form? But if it's an element of T, it's okay.
I don't know. So I really don't know about that answer. That is how mathematicians defined it, and they,
There is some theorem that if we have an infinite intersection of open intervals, we get a closed interval. And if we take our x as r, then that has to be.
But I think that's why we are restricting to finite.
Right. So that is a union.
he is talking about unions. So
No, because you take infinite unions.
Was it union or intersection? It should be intersection.
okay, guys, one by one. So Arush, you have a question about infinite unions lead to a closed interval, something like that.
Meanwhile, when Arush looks up it, should we even tell you?
Could be, yeah.
What's the question?
I will recheck if I have that verified.
So you are asking why it is defined like this way? No, it creates some difference. I can't remember it now.
If we take a excess
Yeah.
original set, then
You don't-
have
You don't need to. Like, it depends on what the other sets are. So you may not get a single point. Okay. We can talk about it at the ending. Yeah. Arush.
Do we have any other questions? Then?
No.
Fine. We can focus.
Can we move forward? Okay. Yeah. So in this topology, guys, in this topology, consider this set C. Is this open? In this topology, it is not, right? Is this closed?
Yeah.
It is closed. For this topology, consider the set. Consider this set in this topology. Is this open?
Yes.
Is this closed?
Yes.
How many are saying no?
It
It is closed also. So in topologies, a set can be both open and closed, open but not closed, closed but not open, and neither open nor closed. Okay?
That answers my question.
Yeah, open and closed are not opposites. Okay. Now let's move forward.
Can you give examples?
Examples of? Yeah, so see the set. This is open and closed. So this set ABC, this belongs to the topology. So it is open, and it's like X minus this set, which it is the null set. It also belongs to the topology. So it is both open and closed. Yeah. Okay. Any doubt, guys? I can construct it somewhere. So yeah, so in this topology, consider the set A. It is neither in the topology nor is it difference with the set X in the topology. So it is neither open nor closed. So let's talk about something called the standard topology on Rn. So this thing really connects to the idea of open intervals where we started. So it is defined some implicitly, it is not defined very explicitly. So a set U belongs to the standard topology in Rn if like it is defined like this. For all points belonging to the set U, there exists a radius belonging to, there exists a positive radius such that the open ball around the point P is a subset of. How many of you don't know about open balls? I will define it. So, an open ball of radius r around the point x is a set of points y belonging to Rn such that okay, so this is the definition of open balls. Do you intuitively see what is this is doing? Yeah. So yeah, it is creating an n sphere around that point and seeing how many, like what all points lie within a distance r to that point, and like that is the set Br. No, I could define open ball without a metric, and I don't really need a metric. There is no distance. Y minus xi. So Rn is r cross r. So I could define the components without the metric. I don't need the metric. Rn gives you a metric, but I am not talking about a metric. Yeah. Any more doubts?
Isn't this equivalent to just the Euclidean metric in R?
Yes.
So what is the difference between saying this and metric?
I am not defining a metric now. Let's move forward. I get your point. This is exactly the metric, but let's move forward. So I will define metric later on, like not even in this lecture, after some lectures. So the standard topology contains sets U such that for all points which belong to the set U, there always exists an open ball around those points which is a subset of U. So if I have a set like this U, then for each point P, I will always have an open ball. This is the standard topology on Rn. Now, saying that something is a topology doesn't make it a topology. So I have a homework for you guys. Prove that this is indeed a topology on Rn. So you have to, what you need to do, so first you need to show that phi belongs to this standard topology, then Rn belongs to standard topology, then take two sets U, V which satisfy this and show that their intersection must also belong to the topology, and similarly do that for units. This is a homework for you guys. I will have a solution in my notes, so you could refer to that also. But what I want you guys to notice here is that all open intervals are open sets in this standard topology. Are you guys noticing that? Open intervals in Rn, or not open, so open intervals in R actually generalize to open balls in Rn, and they are themselves in this topology. So sometime later I will define the definition of continuity in topological spaces. What I want you guys to do there also is to verify that the notion of continuity in topological spaces goes to the same notion of continuity in Rn when you equip Rn with the standard topology. Okay? Any doubts till now?
The last one.
Are you talking about continuity?
For that thing, how the open ball is also a standard.
So just this is, just look at this thing. If I just take an open ball here, it is obviously a subset of an open ball.
Oh, right.
And if I have an open ball and around P, and you have another point Q here, then I could define another open ball here with some lower radius. Like this was done in UM 102, one of the quizzes. I remember that. So all open balls belong to the standard topology. So the open interval idea in R generalizes to open balls in Rn. So all open balls belong to the standard topology. That is just what I am saying. So this is how you relate the two ideas. Now let's talk about continuity. Because this next in minutes. So, say we have two topological spaces, the set X equipped with the topology Tx and a set Y equipped with the topology Ty. Consider a function or a map from the set X to the set Y. Okay, before I define this, do you guys remember the notion of pre-images? Pre-image of a set. I will just write it here. So, pre-image under the map phi of some set V is the collection of all. So, phi, the V belongs to the domain of the function phi, and so you have a map here which maps from X to Y. So you take a set here V on which this notion maps to, and you take all the points here whose mapping gives you the set V. So it is a collection of all such X belonging to X such that phi of X belongs to V. Any doubts with this definition? Yeah. So the map phi is said to be continuous if and only if for all open sets belonging to the topology at Y. So for all open sets in Y, the pre-image of those open sets under the map Y is also open.
Is that Tx and Ty standard or
No.
just regular software?
Like you define the definition, like you define continuity from this between topological spaces. So a continuous map is actually, so you have this set X, a set Y, and you have open sets in it. These open sets in it are basically the topological structure that the topology is describing. The map phi is continuous if corresponding to every open set here, there is like all the points which are being mapped to here also are in an open set in this. Do you understand this definition?
This says nothing about the size of the pre-image or image.
The size of the
Pre-image or image. The span.
why would it need to say about the span?
Isn't that important for continuity?
I really don't get your point. Can you repeat your question?
For continuity, don't we need to get that image gets arbitrarily small as the.
Oh, okay, yeah. So, again, just wait 2 minutes. Just wait 2 minutes for that. So, this is a general notion of continuity for any topological spaces X, Tx and Y, Ty. Now, what Arush is actually talking about is relating how this definition of continuity goes to the known definition of continuity we have known in Rn. So, if you equip the set Rn with the standard topology in N, and map it to some other Rm also equipped with the standard topology, then this definition of continuity is exactly the same as the definition of continuity you know. How does it become same? Because we are talking about open balls here. So there is a notion of difference here. So what Arush was talking about size, the size comes from here. Okay. So in the case of Rn and Rm equivalent with standard topologies, you get the same identical picture we had before. Any doubts? Someone thinking what is going on here? Someone else thinking what is going on here except Aviru. Okay.
To motivate this better. If you have anything.
Actually, I don't, because this is like purely mathematical abstractness, and I have tried to motivate as much as I can. Okay, so suppose I have the set Rn equipped the standard topology on Rn. The standard topology was defined there, and I have another set Rm equipped the standard topology on Rn. And if I have a function, or not a function, if I have a mapping Rn to Rm, and phi is continuous with in this definition, that is phi is continuous if any open set of Rm has its pre-image as an open set in Rn, then this definition of continuity is the same of the same definition which you read in multivariable calculus. That was the point, and I am not going to explicitly prove that because this is not a math course, but I will attach its proof in my notes. Okay. So a map is continuous if pre-image of open sets is open. Now let's move forward. I will give you some examples. Okay. So consider this function. So consider set X, and the topology we are equipping the set X is the power set, and it maps to some set Y, and it has some topology Ty. Now I claim that any function like this is always continuous. I will give you guys like 1 minute to think about this.
Every pre-image is always set in class.
Yeah. Can people see this?
Every pre-image is part as an element of the power set.
Yeah. So it is open. So it is there. Yeah. Any doubts? Is everyone able to see this? That this function is always continuous. Okay. We are very short on time. Okay. Now, so while you studied vector spaces, you studied about linear maps, right? So linear maps are maps which map linearly from one vector space to other vector space. But what was the importance of those maps? They were structure preserving maps in vector spaces. So you could relate all the vectors and the addition and multiplication functions there to another vector space, and in such a way that your information did not get destroyed. Are you understanding the point I am making? Somewhat, like. Okay. So similarly, for these topological spaces, we have maps called homeomorphisms, which are structure preserving maps in topological spaces. So homeomorphisms, I will call them homeo. So let phi be a map from set X to set Y. X is equipped to the topology Tx, Y is equipped to topology Ty, and you are given that phi is a bijection. Okay, So phi is homeo when phi is a bijection, phi is continuous, and phi inverse is also continuous. So phi is a map from set x to y, phi inverse map from set y to x. Because phi is a bijection, we could define phi inverse. And once we define phi inverse, we could check for its continuity. If that phi inverse is also continuous, then only we can say that phi is a homeo. So what this phi actually does is, so you have this set x, set y, some open sets here, some open sets here. Because of these definitions, these open sets get mapped one to each other. Not only the points get mapped to one another bijectively. So points are getting mapped to each other because it's a bijection. It is a one-to-one onto map that basically maps each point to another. But because of these two, all the open sets are also getting mapped to one another. You guys can see that.
And then every point in that open set is getting mapped.
Yeah.
And back.
Yes.
Isn't that directly following from bijection?
No. Because bijection doesn't say anything about.
Bijection says that it's one-one onto map, right?
Yeah,
So
but-
every point in that open set will be mapped.
Will be mapped to somewhere there, but that may not be open.
Okay. The existence of
The
phi inverse being continuous means that will also.
Yeah.
Right?
Because we need that phi inverse is also continuous since x and y dx into y need not be the same, right?
Sorry?
The third condition, we still need that and it's not trivial since x and y need not be same, right?
Yeah.
It's not r and y.
Yeah. So you are invoking some sort of dimensions here.
Not necessarily dimensions, but in general.
Yeah.
It might be some other set.
So from this you see that homeos are actually structure preserving maps in topological spaces. So I think most of you have heard that a donut is similar to a mug. A donut is similar to a mug, right? In this sense, they are similar. There exists a homeo from a donut to a mug. Okay.
Why not? Aren't homeomorphisms the same as isomorphisms? Or is there any difference?
Isomorphism just involves a bijection and continuous, right? I don't think it involves this statement.
Isomorphisms must also be structured together.
Isomorphism in what?
Uh,
Isomorphism is there in sets, right? And in sets, like the isomorphism maps need only that the function is a bijection. It does not invoke continuity. Continuity is only defined once you define a topological space and once you define a topology on the set. And once you define topology, you could define continuity and then you could define a homeo.
And a correction to isomorphism sensibility.
आइसोमॉर्फिज्म हाँ ग्रुप्स में तो होता है सेट्स में क्या होता है कुछ कहते नहीं है ओके
As well as I.
I had heard the definition was structure preserving matrix.
like they are
But like they're mostly used in different contexts.
yeah so structure preserving maps in vector spaces are linear maps like they okay okay now I wanted to define some topological properties but seeing that it is already 10:30 I will just define one which I need afterwards. Okay, before that, so given given some set x equal to the topology Tx, you could induce a topology on its subset. So Like say you have a subset, you have a set A which is a subset of X. Given this topology on X, you could induce a similar topology on A. How? Like you just define the topology at A, I will just write you at T, such that take all open sets belonging to the topology and just perform their intersection with it. So you have a set X and it has a topology, at least it has some open sets like this, and you want to induce a topology on its subset, like a set like this. So what you do, you just take the intersection of this set with all the open sets. So this becomes a new open set, like this becomes a new open set, this becomes a new open set, this becomes a new open set, something like that.
So does A have to be an open set?
Not really.
If not, then T and A need not have A.
Take intersection of X with A. You get A, right? Yeah, I was just going to that. So you need to prove that TA is a topology on A. So for that you need 3 points. The definition of topology basically. So to prove that phi belongs to TA, just phi is an open set under X. So phi intersection A is phi. So phi belongs to the topology at A. X is an open set under X. So X intersection A gives you A, and A, so A belongs to the induced topology. And similarly, you could do the same for unions and intersections. Can you guys complete the proof? I will attach it in my notes also. Any doubts? I see a lot of questioning faces. Any doubts, then speak up. So no doubts? I will move forward. So I will define a property of topological spaces called Hausdorff. Hausdorff is a type of property in topological spaces. You can always define, like for every set there exists a power set, and X comma power set belongs to the topology. So by ZSF, the power set is always a set. Yeah, that is one of the ZSF axioms. Yeah, so consider any collection of subsets of the set. Yeah. Okay, back to this Hausdorff. So Hausdorff is a topological property belonging to a class of topological property called separation properties. So it tells you that 2 points in the topology are some sort of separated from each other. So let X comma T be a topological space. This is Hausdorff. If for any 2 points, any 2 distinct points, P comma Q belonging to the topology, there exist non-intersecting open sets around these points. So belonging to the set X. Yeah. So we have a set X into the topology and consider 2 points in the set X. So the topological space is Hausdorff if there exist two open sets U comma V such that U contains P, V contains Q, and U intersection V is phi. So, given a set X, what this thing is saying is, for any 2 points P and Q, you can always find open sets such that you can always find open sets U and V such that U just contains P and Q V just contains Q and their intersection is the other set.
U and V should be P.
Yeah. They are open sets. Okay. So, why we need this sort of thing? So, to tell you why we need this, I would have to give you a little bit intuition of how convergence is defined. So, I won't define it rigorously. Like I won't even give you a definition of convergence, but a sequence. So you all know what a sequence is, right? A sequence is a map from natural numbers to the set. Like the set we are considering here is X. It's a sequence like A1, A2, A3, A, N, so on. So this is a map which takes natural numbers as input and gives you an element in X. So a sequence in X is convergent to some point, call that point Q. So the sequence Fn converges to point Q if for every open set containing Q, if like for every open set U that contains Q, for all U containing Q, there exists some natural number n such that for all n greater than n, the sequence belongs to this set. So I will draw a picture for you. So say you have a point Q here, and you are saying that your sequence converges to this point Q, and you have the sequence like this. So the sequence will converge to the point Q if for every open set that contains Q. So there will be many open sets that contain Q, right? If for all those open sets there exists a natural number n such that all the points after that natural number n belong to that open set. Like for this set, all the points after this thing belong to this open set. Do you get an intuition for this definition? Like, I won't cover it very rigorously, but an immediate consequence of this definition is that the point where the sequence converges may not be a single point. So suppose you have another point here P, which contain all the same open sets in which like the Q has. So you have a general topology, and the P and Q points occur together in the open sets always. So if a sequence is converging to Q, it is also converging to P. Do you guys see that?
The capital N that we have to take for converting to Q, and then for each of these open sets.
There exists some N.
Yes.
You could take any N.
So when it converges to Q and when it converges to P, the N's might be different.
Yeah. So what I'm saying is, like, if the points P and Q always occur together in open sets. So
in all the open sets that you have, both P and Q exist.
Yeah, not all the open sets. All the open sets which contain P also contain Q.
Also contain Q, yes.
So if a topology is like that, and I'm saying that the sequence converges to the point P, that automatically means that the sequence converges to the point Q. Do you guys get that? So now what this Hausdorff does, yeah,
अगर दोनों point if both the points are in the open set, then it won't factor that stop.
yeah, I am coming to that. So if the topology is Hausdorff, then this thing can't be true, because Hausdorff always restricts that there is always open sets in the topology which contain one but not the other. So a convergent sequence in a Hausdorff topology can only converge to one point. This is why we need that, because in physics, like, you really want that. Suppose you have a truck moving with some velocity and it's deaccelerating. You really don't want it to stop at 2 points simultaneously. So you need this thing. Oh,
Can you give an example? Can you give an example for a topology is not Hausdorff?
yeah. So I gave some example here, right? For the set A, B, C. Yeah. So consider this set ABC as M and the topology T as the set A, the set BC, phi and M. So you see B and C always are together. So this is an example of non-Hausdorff topology. Okay. So I wanted to discuss another topological property called compactness, but as we are already at 10:40, I am not going to discuss it. You can find it in my notes, okay? Like, I haven't been to 1/3 of my notes yet.
What is not meant for just it?
Yeah. So now let's come to manifolds. First, we define topological manifolds. Okay, I will try. So basically, a topological manifold is a topological space that locally looks like Rn. A topological manifold is a topological space that locally looks like Rn. So, like, consider this: the surface of a sphere S2. Like, I will just color it for some intuition. This set in, like, I won't go to very much rigor here, but this set, like, at any point you could attach a grid here, so it locally looks like R2 at any point locally. Yeah, I will come to that after some time, but like, the surface of Earth is like S2, and this room, it locally looks like R2, right? From what you are seeing here, it looks like a plane. So that is what I mean by locally look here. So topological manifolds are objects like that. So it can be a surface of a sphere or a surface of a torus, anything like that.
Locally for every point.
Yeah. I will give you a more rigorous definition. So, definition. A Hausdorff paracompact topological space X comma, I will write it now M. Okay, M comma, the topology is denoted by O here. Okay, I have changed the notations. I will write the set as M now and the topology as O. Okay, is called a d-dimensional manifold by manifold. I here mean topological manifold. Okay, if for every point belonging to the set M, if for every P belonging to the set M, there exists an open set around P. There exists an open set U around P, like by around P I mean containing P, such that there exists an open set around P and a homeomorphism X which takes from U to X of U, which is a subset of RD. Okay, a very long definition, I will explain it now. First of all, just ignore this word. You will, like, if I try to explain this, it will take 1 more hour, so just ignore it, okay? All sets or like all spaces in physics which you will encounter will be paracompact, okay? So, I will give you another thing. Like, most of the spaces which we encounter in physics are metrizable. Like, those of you who don't know what a metric is, just ignore my statement, okay? And all metrizable spaces are paracompact. So, just take my word for it that whatever you will encounter in physics will be paracompact.
Metric just space where you can define a distance.
Yeah. You can define a notion of distance. Okay. So the topological space MO. Yeah, I am explaining the whole thing. So, a topological space MO is a d-dimensional manifold, a d-dimensional topological manifold. If first of all the space is Hausdorff, the space is also paracompact, but we won't worry about that. If for all points in the manifold, if for all P belonging to manifold, there exists an open set, but like I will just now say open set, I won't every time write that it belongs to the topology. Like whenever I say open set, just understand, okay? There exists an open set containing the point P and a homeomorphism which maps the open set U to like this is how we write range basically. This this homeomorphism maps the set U to some subset of RD. Okay, so you have a set U here and you have RD here. This set U maps to RD, and if we just take the set that it maps to, like I will call it X of U, the range of X basically, the range of X, then this X is a homeomorphism. That is, it maps 1 to 1 here, it is onto, it is continuous, and its inverse is also continuous.
For the we take the standard topology for the range of homeomorphism.
What do you mean by range of
What
homeomorphism?
do we take as the topology of the homeomorphism?
Yeah, standard topology, correct. So yeah, I should have mentioned here. Yeah, this is more standard art. Okay, nice pointing that out. Okay, guys. So now come back to this. So by this definition, what I'm saying is that for each point P on this set, there exists an open set here which maps to, in this case, R2, which maps like this, and such that this map, I will call it phi, this map is a homeomorphism. Like this is a structure which I map, so it maps without loss of any information. So
Between three-dimensional and manifold, what is that?
topological map. Like here it obviously means just like it's called a d-dimensional topological map.
So do you mean all manifolds are Hausdorff? Do you mean all manifolds are Hausdorff?
All topological manifolds are
There can be non-Hausdorff.
not topological. And I don't know how manifolds are defined other than topological
Now,
manifolds.
you take a real line, so the origin and to new origins. This map to different. This map to different tracks. It can be non-Hausdorff.
I don't know. We can discuss later. Okay. Can you speak a little bit?
How do you typically define a topology on a surface of a
Yeah, so you basically cheat a little. So this surface S2 is like it is embedded in R3, right? Like you could take a sphere S2 and its surface is like the surface lies in R3. So from R3 you induce a subset topology on S2. I told you about subset topology. Yeah. So or like you could again define and something like an open wall here.
It's not defining the normal open wall for R.
No. So basically you cheat a little.
Nothing will be.
Yeah. So when I'm saying that S2 acts like a topological manifold, I am saying that S2 equipped with that topology which it inherited from R3. So the basic topology that all sets containing like near to this point are form an open set. Should I explain this statement again? Okay. So S2 is a subset of R3. Like it is not actually a subset, but it can be thought of as taken like embedded in R3. And R3 is equipped with the standard topology. So I told you how to induce a topology from a bigger set to its subset, right? So using that, you could induce a topology from R3 to S2. And it would be like, do we have a spherical thing here? I don't have a spherical thing here. So for any point P, like you could draw some epsilon neighborhood on like something like an epsilon surface here. Like an epsilon, not a straight line but a curved line, something like that, and that would be an open set. Like
You mean we are saying all this just because we cannot define a like standard topology on S2.
Yeah.
Right.
So
For defining a standard topology, we need RT.
yeah, so we induce some sort of a standard topology on S2 using a topology on R. So S1 is a circle if you take Cartesian product of two circles, get a sphere. If you take Cartesian product of three circles, you get, I don't know what is called, but it is just S1 cross S1 cross S1. So, like if you take Cartesian product of two spheres in some other sense, you may also get a torus. So this torus is also like two circles orthogonal to each other. So that is why I have written S2. S2 is not exactly S1 plus S1. S2 is S2 is a sphere, surface of a sphere. S2 is the surface of sphere. S1 cross S1 is a torus. So corresponding to each point of torus, you could define two coordinates, like one with corresponding to this circle and one corresponding to this circle. So like you could write any point in torus as some sort of Cartesian product of 2 points on circles. Sphere is called S2. Any doubt in the definition? Can I move forward? Okay. So one immediate consequence of this definition is that the dimension of manifold is always well defined. Like if so, consider two open sets U comma V such that their intersection is non-zero. Okay, their intersection is not null, like they have a finite intersection, and consider some, like we are examining around a point P which falls in common to this, like which falls both in U and V. So which falls in U intersection V. So the map X from XU, this is a subset of RD, and Y V to Y of V, this is a subset of RD dash. From here, as this is not equal to 5, we could immediately see that D must be equal to D dash. So dimension of a manifold is always well defined. So what I am saying is that the dimension of a manifold is always like well defined. By well defined I mean like it is not, the dimension is not a local property. The dimension is that of the complete manifold. How you can see that is consider two open sets nearby such that their intersection is non-zero. So now this thing maps to some RD, this thing maps to some RD dash. So this thing also is a homeo to RD also, and it is homeo from R to RD dash also. So it is a structure presuming map from R to RD and also to RD dash. That means D must be equal to D dash. Because if you change the dimensions, you change the information.
You have already proven the structure of RD and RD dash are.
Yeah.
They don't even. We don't know there's no automorphism between RD and
No,
RD.
they are not. You could project one space to another, but like you can't have structure with a wing man between those. Yes.
Doesn't it operate in different dimensions for elements which are show the intersection?
No, so you could like this is same dimension. Now consider here this and this and you go on. Yeah. Okay.
We are not actually proof that we are not actually getting the
So now let's come to the concept of charts and atlases. Like these form a very important concept in study of manifolds. So guys, calm down. M comma O be a topological manifold of dimension D. Then a pair of a set U and a map X, where the set U is open, that is, it belongs to the topology, and X is the map which we talked about earlier. X goes from is a subset of RD. This pair is called a chart. Of the manifold. Okay. So the pair of the open set U along with the homeomorphism which maps it to the set RD, like to the subset of RD, is called a chart. Okay. So chart is just an open set along with the map which it homeomorphically maps to a subset of RD. Now, as this is mapping to RD, and RD is like R cross R cross R, D times. So we could define projection maps to each of these R. So component functions. So we could define component functions of it. Component functions of F of X. They map from U, this set only, to R. Like this thing maps to X of U, which, but like I'm enforcing it to map to X of U only because I need this as a homeomorphism. If I could also think of it as mapping directly to RD, then the only thing that will happen is it won't be a bijection, nor it. So if it is not a bijection, it's inverse what we defined. But still, I could think of it as mapping to RD also, right? I'm enforcing this thing here because I wanted it as a homeomorphism. So if we take X to map to RD, then each of the components of X map to an individual R, such that Xi of P equal to the ith projection of X of P. Okay? Ith projection means like if like in RD it is like this, then ith projection takes out the element Xi. And note that this is with respect to the chart Ux. So this notion of components is not independent of the chart. It depends on what chart we are using to map the point P. Any doubts? So this X depends on U we are choosing. So this notion of component functions is not at all independent of this chart. So these component functions depend on the chart we are using, obviously. So like in R3, if you have 5, 2, 3, then its components are 5, 2, 3. That's what I'm talking about here. So if you have the like x vector as this thing, then its components are x1, x2, xn. The ith component would be xi. That's just what I'm talking about here.
The dimensions of U and X of the U are the same.
Not at all.
So
No, wait. Yeah, they are same. So X of U is a subset of RD. So as it's a subset of RD, it obviously has a dimension D. U is defined to be dimension D. U is a like not U. So dimension of U doesn't make any sense. But the dimension of M is D. And U is an open set of M. So U is a subset of M which also belongs to the topology. So like in a way you could say that U has dimension D, but I don't think we really talk about that.
Then how many components would like
So components are like once you map it to XU, this always has D components, right? Because it is a subset of RD. This has D components. So it will always have. Now, so we have these charts equipped in the manifold L. So obviously there exists a set A called atlas of the charts such that union of all the open sets U comma X which belong to the atlas A is equal to M. This is the definition of atlas. So atlas is a set containing charts such that the union of all the open sets which atlas contains is equal to M. It can also be like this is M is a subset of this, but for our purposes we will just take it equal. Okay? Yeah. So, yeah. Like at least what I will give. I have to find.
Can't use open sets defined on the coordinate data.
Yeah.
So how exactly is the union percent?
Like, so, no, wait, they can't. They can't be, right? Yeah, they can't be. It is actually equal to M. In some other context of defining atlas, you get other definition, like a subset, but I think in this case here, you will get equal only. Yeah, so this is how we define atlas. Any doubts? Like, Arush, I see a very confusing.
Here is all my doubt. The maths is fine, I'm just confused with what we are doing.
defining stuff? They're defining something else.
Yeah, so this lecture is basically defining stuff only. The next lecture we will actually use the stuff because we actually need to go to smooth manifolds, and smooth manifolds is the language on which we do general relativity. And to go to smooth manifolds, you have to define all this stuff. Okay? Like I will define a lot of more stuff now. So I define an atlas like this, okay? Now obviously when I just take a union here, there might be some charts which have there might be some charts U and V in the atlas such that their intersection is not null. So there might be charts which do not which contain some same collection of points. Okay. Now we'll so again another definition. Here I will talk about this thing. So two charts Ux and Vy are said to be C0 compatible. For first of all, do you know what C0 means in like Rn? It just means continuous. It is just a fancy way of saying continuous in Rn. Yeah, it is a set of continuous functions. Are said to be C0 compatible if either we have U intersection V equal to phi. If first, like they are obviously compatible if they have no intersection. If they have no intersection, they don't have anything to disagree about with each other. But if their intersection is not null, then so I will give you a picture here. So this is our manifold M. We have two open charts U, V, such that their intersection is non-zero, and we have a map X which takes this to some RD. So U gets mapped to some X of U in RD, and V gets mapped to some Y of V in RD. Okay? And this thing, U intersection V, so when it goes through X, it goes to something like this here, X of U intersection V. Like all points in U intersection V goes to here. It may not go to like collected together, like it may go to different spots, but I don't care about that. And when it passes through here, it goes to Y U intersection V. Now the maps are compatible if we have a mapping from here to here which is continuous. You get my point? So I will explain why we need that in like just 2-3 more minutes, but let me complete this picture. So say we have a point P here, X of P goes to some point here, and X, when applied on X of P is some point here, and when we apply Y on it, Y of P is some point here. Then Y O X inverse is a map from here to here, not here to here, sorry. It is a map from here to here. It takes X of P as its input and gives Y of P as its output. Now I am saying that so these maps are compatible only if this function is continuous. Why we need that? So in physics, so you would define a similar map X over N. So it is already a bijection. This map is already a bijection because this is a homeo, this is a homeo. So this map is already a bijection. But so inverse already exists. If we we need that also to be done. Y X inverse also. So why we need this? So in physics, we want our picture of reality to be coordinate independent. So what we are doing here is like suppose you are investigating the motion of a particle on a surface of sphere. Like on the surface, like you have the earth surface, a car is moving along. You are investigating the motion there. So what do? You take a local patch here, map it to R2 and say it is moving on a surface. Now I could also take another patch just like close to this, and I could also investigate my physics there. So, and this function from the first patch is continuous to R2, and this function is also continuous to R2. But in that area which is common, I need a common transition. I need a continuous transition map which goes from this area here to area here. Do you get for my physics to be coordinate independent? Otherwise, my physics would depend on the charts. It will depend on what charts I am choosing. I don't want that. So I want my maps to be compatible, so I could simply go from a space here to a space there by using this map y of x inverse, which is continuous. Do you guys get my point? Third row. Right. Okay. Any doubts? Okay, I will move forward. I don't see happy people. Do you guys want me to explain something more about these things? So yeah, a lot of these things are abstract. I get that, but I really can't help.
Can be the other way around.
Yeah, it can.
View to x, y, b. Maybe x of b to
It could be other. You're right. That is actually what we talked about. Now, another definition, but a very small definition. An atlas is said to be maximum. So first of all, an atlas is said to be C0 if atlas is C0, if any two charts in the atlas are C0 compatible. Okay, so atlas is a collection of charts. It contains many charts. If any two of those charts are C0 compatible, then the atlas is C0 compatible.
Here, any is for all rather than there.
Yeah, for all.
No matter what we do, it has to be.
Yeah. A few more points here. So, like one more thing, like which I wanted to talk about, but I skipped there, guys. So, I was talking about y of x inverse. First of all, it is called coordinate chain map, and in the case in which M is a topological manifold, like M is not a general topology but a topological manifold, this map y of x inverse is always continuous. Why? Because x is a homeo, so it is continuous and it is bijective. So x inverse is also continuous and it is bijective. So I will paint a picture for you. U intersection V, x maps to x of U intersection V, y maps to y of U intersection V. Now I want to go from here to here. To go from here to here, I can go first back x inverse, and then I can go from here to here. So what I did was first did x inverse, then did y. This is basically y of x inverse. This maps transitions from here to here, and this is continuous. This is continuous. Composition of two continuous maps is continuous. So in case of a topological manifold, this is always true. So any atlas in a topological manifold is always C0 compatible. Okay, any two charts in a topological manifold are always C0 compatible. Do you guys get my point? Okay. I am not writing this definition. Okay, you got my point, right? So another definition: a C0 atlas is called maximal if any chart u comma x which is compatible with v comma y belong to the atlas is already in the atlas. So a C0 atlas is a collection of a maximal C0 atlas is a collection of charts such that if you have a chart in the maximum atlas and it is compatible with some other chart, then that chart is also in that. So in a sense, it contains all like the maximum, like that is not mathematically rigorous, and Akhil will point that out to me. Like, in a sense, it contains the maximum amount of charts you can get in an atlas without losing the C0 without losing the compatibility. Guys, got my point? So suppose you have a C0 maximal atlas. Then what does it say is that suppose you have a chart Vy belonging to the maximum atlas. Then any other chart u comma x which is compatible with this V comma y is already in that atlas. Like, it is also in that atlas. Okay.
Will it be equivalent? Like, if I say that a C0 atlas can be called maximal, if if I have any other C0 compatible atlas, that will be a subset of this.
Repeat the last point. That is a subset.
If I have any other C0 compatible atlas on this topological manifold, it will be a subset of this particular atlas.
Yeah, you are correct.
It is the same.
If the chart in the
Yeah, so
if it is for any chart in the list or just any single chart.
So
That is already compatible and all are already compatible.
should I need to explain?
One more thing.
Yeah.
Is compatibility if two charts A and B are compatible, B and C are compatible, are A and C also compatible?
Yeah. You could define, like, you could write it right here.
Compatibility is from the top.
Yeah, you can go. Like, you could do a very similar thing from here too. Yeah. Any more doubts? Can I teach for?
Suppose you have two charts in there, but such that U and V are disjoint, so they are automatically compatible.
Yeah.
However, there is some other chart such that it is not disjoint both U and V, but it is compatible with one but not compatible with the other.
So, if you have a topological manifold, then any two charts are compatible. By compatible here I mean C0 compatible. Later I will use C infinity compatible for differentiation. For that this won't hold true. But in a topological manifold, any two charts are compatible. So, like, the maximal atlas statement is trivially true there. Like, you have them as compatible. You can't have two C0 uncompatible charts in a topological manifold. C0 I'm talking about. You can have higher CK uncompatible charts. Because I told you here, right? You could always, like, when you want to go from X, this subset to that subset of Rn, you could first take the X inverse, which takes you to the manifold, and then take Y on that. This is continuous, X inverse is continuous. Composition of two continuous function is continuous. So this composition is always continuous.
There are two different charts, both are disjoint, they are compatible. But then you have a third chart, which is not disjoint with either. But it is compatible with one of them, but not compatible with the other.
Yeah, that's what I'm saying.
U and V are disjoint, so W is not disjoint with U, and W is not disjoint with.
So in case of C0 compatibility, the charts are always compatible. But if you don't have C0 compatibility, then the transitivity does not work. Okay? Like, if you are not talking about C0 compatibility, if you are not talking about topological spaces, then the compatibility does topological manifolds, then the transitivity does not work. Okay? I really wanted to introduce differentiable structures today, but
C0, C1, C2, C3, this is a set of.
yeah, exactly.
This is a vector for the small function, which is 0 is just continuous, 1 is just one differential.
Yeah. The first derivative is continuous, the second derivative is continuous. Yeah, C infinity is smooth. All derivatives are continuous. I will come to that. So now we'll finally give you an intuition of what we are doing. So in physics, like, we are concerned about trajectories of particles. So a trajectory is basically a map from R to some space M, some manifold M. R is basically denoting time. So trajectory is gamma as a function of t, right? Like suppose a particle is constrained on a sphere, the trajectory it follows, something like this. So it is a gamma as a function of t, right? Now, and M is a general manifold. So we restrict ourselves in looking at some open neighborhood, at some open set around the time we want to think about. So, like, suppose the particle is going here. Suppose the particle at some instant is here. So it is going in here. So it is going like it is confined here locally. So I will talk about a smooth set, an open set U here. Okay. So I have some open set U in the manifold M, and I have functions which take it to x of u, which is some R. Like I have some open chart x of u. And we have this gamma here also. Gamma maps from pre-image of u to u. I am just enforcing it to be pre-image of u instead of reals, so that I could make this bijective. Nothing else. Okay? I could take this as real also. Like this is a subset of reals. So what we actually think while solving the problem is about this map x o gamma. We very rarely think about maps on the manifold. We actually always think in terms of coordinates, right? Like here you think in terms of coordinates of sine theta cos theta. So sine theta cos theta are basically mapping this surface to some R2, to some constrained region of R2, and you are thinking about the physics there. You are thinking in terms of coordinates. So what we are actually thinking about in physics are these maps x o gamma. But you see, when we are thinking about these maps, the physics is automatically constrained, like the physics is already dependent upon the charts, and we don't want that. We don't want our physics to be dependent upon the coordinate system we are taking, the charts we are taking. So suppose we have another chart on u only, like y comma u comma y. So if there is not another chart on u which is y, like take another set that has non-null intersection and replace u wherever I am talking about with u intersection v. Okay, that is trivial. So suppose I have another chart y which maps to y of u, which is a subset of Rd. And if I go to this chart, then I am talking about this function y of gamma here. Now, as we discussed there is a way to go from here to here. That is that map y of x inverse. The coordinate transfer map, the chart transfer map. We discussed it there. It is continuous. So the existence of this map make continuity of this gamma in that manifold well defined. You get my point? So we are thinking about the continuity of the function of this function and this function. We don't directly think about continuity here and here and here. Why? Like we don't think about continuity directly here. Why? Because we know that any chart we use is always C0 compatible. That is, there is continuous transition map from the set we are like the set we are using here to another set. But if we talk about differentiability, like suppose now I want to know the speed of a particle here. The speed of the particle involves differentiation. So I need to, like, I can define differentiation on this map X. I could also define a differentiation on this map Y. But the transition map doesn't has the structure of differentiability yet encoded in it. We showed that the transition map is always continuous, but we never commented about its differentiability because we can't unless we give this manifold, the structure of manifold, a more structure to it. Like we now enforce our maps to be C1 compatible or C2 compatible or C3 compatible and so on. Then only we could talk about differentiability. Otherwise, like you could obviously encode some differentiability in some chart X and talk about physics there. But then physics will be dependent upon the coordinate system. And that is non-natural. We want our physics to be independent upon the coordinate system. So we need to give some additional structure to this chart transition maps. And that structure is given by what is called a smooth manifold. A differentiable manifold basically, but we will talk about only smooth maps from now on. Smooth maps are maps which are C infinity. That is infinitely time differentiable. And every derivative is continuous. We will only talk about those kind of functions. Okay? Can I teach for like 25-30 minutes more?
I guess no for the first.
Okay.
Because there is a lot of material.
Okay. Okay, guys. Then in the next class we will talk about the smooth manifolds. It will be covered in like 25-30 minutes. Then we will go on to tensors and then tangent vectors. From tangent vectors, actually the physics will start coming. Okay. Thank you.